Let me introduce the person who will be the chairperson of the symposium panel on resources and the environment in the new millennium. I'm afraid we have another change in the schedule in order to accommodate Professor Mesarovic's need to leave early. Professor Simonovic will be the chairperson, and we will introduce Professor Mesarovic first. He will give his brief remarks, and then we will follow with the other two presentations after that. So it's just a slight change, but otherwise the symposium will be as originally planned. So let me introduce the person who will be the chairperson for this. Professor Simonovic is the professor and director of the Natural Resources Institute in the Department of Civil and Geological Engineering at the University of Manitoba. He's had 25 years of research, teaching, and consulting experience in water resources engineering. His primary focus is on the application of systems approaches to water resources systems. So here is I think, a clear example of the ability to apply systems thinking and systems methodologies to the imperative environmental and population problems that we face. In addition to some 190 publications in this area and involvement in numerous organizations, he's particularly has been involved with the International Water Resources Association, the International Association of Hydrological Sciences, and UNESCO, the International Hydrological Program. So he's been very active in the public sector work. I am delighted to introduce Professor Simonovic.
Peter, thank you very much for the introduction. This is one of the unexpected occurrences. I was not supposed to chair this session. I was asked to help Professor Mesarovic meet his schedule. So to save some time and give our speakers, including myself, enough time to share with you our experience and ideas, I would like, and I'm quite honored to introduce Professor Mihajlo Mesarovic. I'm probably one of the rare people who can correctly pronounce his family name. Professor Mesarovic is coming from the Case Western Reserve University from Cleveland, Ohio, and I think many of you are very familiar with the work he has done. He's over there, the Cady Staley Professor of Systems Engineering and Mathematics. His areas of interest include the formal general system theory, multi-level systems, global modeling and analysis, and I think numerous contributions, publications, books in these areas are quite widely recognized. Professor Mesarovic will be sharing with us today the presentation and his views of the global issues as a major challenge for general systems. Professor Mesarovic, please.
I'm very glad to be invited to give a brief presentation. This is the first time I'm attending this kind of conferences, and I now see what I'm missing. Not only what I have learned, but also I have seen what other people are doing similar to what I'm doing. So there is a network relationship here. My principal objective is recruiting. I would like to recruit system science community to address some major global issues problems. Not only to help you do some research which is exciting, but because these people need you. And they know they need you, but they don't know why they need you, nor do they know who you are. In a sense, I'm following President Tronkel's challenge. What can you do for these kind of problems? So, since I have only 15 minutes, I will go very quickly to highlights, as well as to indicate what I have been doing. I don't want to say how long, 20, 40 years, whatever, in this kind of area. So, first of all, we have to realize that not all global issues are the same, right? There are 4 categories. One is global commons. Everybody knows that global climate is a global issue, right? Then the second is stewardship of resources. Canada, United States, Argentina, and Australia, they are stewards of world food resources, just like Saudi Arabia is steward of oil resources, and so on. Now, population is not quite clear. Population is a global issue in the last analysis. Why we or Swiss people and so on should care about what's happening? This is through what's called from global problematique. That is, it propagates through other aspects of development. And finally, there is what's called a nuclear bomb of the 21st century, financial market. It can ruin a country in a couple of weeks, as if the country has lost the war. So what I'm saying is there are all these global issues, and they desperately need holistic view, because on the top of all these categories, there is what Club of Rome calls global problématique mondiale, meaning this is all interrelated, right? Very system science. I would like to be a little bit more specific, not to put a challenge which is very difficult to meet. Somebody said to be successful, you have to work on important problem, and something is doable. Let me tell you something that is doable. There is a global climate change community. They call themselves global change, meaning that there is or to what is involved in global issues. And what they said, and Berian actually started his work at Cade with me and so on, they said, finally, this year they realized that they need systems approach. That without systems approach, they cannot make progress. And this is what they're going to focus. Then their science advisor and so on, a key person, defined what he means by that. Global analysis, integration, and modeling. What else is new? Is that what they think about system science? Right? And in this community, where there are thousands of people, where billions are spent on research, it is hard to find a system scientist who is actively involved, not just talking in this kind of research. So this is a slide from a speech by Jane Lubchenco, who was president of ISSS. I don't want to go through this. It's just enough perhaps to say that according to her, humankind is using 2% of photosynthesis directly and up to 30% indirectly, leaving to nature only 70% of photosynthesis. And with doubling of population, it's easy to see that human is dominating the earth. Without going to you don't need models. You don't need to go into any. That fact is enough, right? Now, in global climate change, they talk about human dimension of global change, meaning how people are using land, what is the attitude people to environment, and so on. But humankind is like atmosphere or ocean or animal kingdom, a subsystem, part of the whole system. It has to be taken a systems view of societies, of individuals, as well as in the nature. It's not human and nature. Human is nature, right? And this is not human dimension. It is, again, something which has to be looked in a systematic way. Now, let me show you briefly where the system science, or if you like, theory of general systems, which I have spent one of my lifetimes working on, comes in. I don't care what we call things, but I care whether this is clear what we mean. Right. So I start with the notion of system as a relation on items, which is mathematics, set theory, universal algebra, and so on. But never mind. Then I define a complex system as a relationship on the systems themselves. Units which are related are the systems. Now, to you, this is quite obvious, right? And I'm not saying this is the definition of complexity. I'm saying I start with looking at global issues from this notion of the complex system. So immediately, as you all know, there is a concept of hierarchies and multilateralness, And there are at least 3 concepts of hierarchies which are important here and are related with some other things discussed before, like do we need to use a functional representation of a system or just input-output representation of a system? A first certification is, classical from Balding and whatnot, and other people, a representation of all the aspects of reality you have to take into account. In our global modeling, we start on the top with individuals, with the values and culture. Underneath this are social organization, formal and informal organization. Underneath these are abstract numbers, economics and demography. Economics is, of course, a system invented by human for resource allocation and accounting. Underneath this is technology and environment. So this is already a model, a structural model. It's not numbers, right? But it is already a model, the first view that you take. Now, the important thing about a hierarchies, and let me go back to the distinction between system and complex system. Limits to growth. But the problem with that view is that the globe is viewed as monolithic, meaning a pendulum, right? But actually, global systems exist only because subsystems are interacting through globalization. So looking at the globe as consistent of subsystems with interactive give you completely different behavior. Globe might not collapse. Africa will. But Swiss will enjoy their life. And so will Americans. So what I'm saying is it makes a difference whether you look at the globe as a system, which I don't think exists, but as a complex system, that is globalization processes and so on. So what I'm saying is this already is useful. You don't have to apply system science in the sense of turning something that comes with a number. Giving a perception, a paradigm is already there. In the general systems theory we are talking about, we look at contribution of general systems theory in terms of paradigms, in terms of architecture, in terms of structure, and maybe numbers. Okay, now the second notion of, here. The important thing here is that these levels are not integrated. They are related, and in normal conditions, they are independent. In other words, they are stratification. Under normal conditions, the levels are independent. When everything depends on everything else, this is a sign of trouble. When these levels are. So system science should perhaps look into what is the degree of independent behavior. You have this in human body, you have this everywhere, right? And this is perhaps what Professor Zwick was talking about, imprecision. I wouldn't call imprecision. I would say essential uncertainty, which actually makes the system behave. Organized complexity, if you like. Now, the second hierarchy, which is extremely important, is hierarchy of functional behavior. I call it goal-seeking, whatever you want to call it. And essentially, there are 3 steps in order to describe a system, 3 elements. One is, what is the view of the system of what's happening? And what is the function which he or she uses to measure performance? The second is what the system knows about the environment, and finally is what it does. Let me just quickly describe this. No. Never mind. So what I'm saying is there is a self-organization which is really changing the structure of image of the world as well as how you evaluate the consequences. There is a level of adaptation when you adapt to the outside world, and there is a level of actually making decisions. Now, this is important because humans are not machines. Humans are not input-output. Humans are not rats or pigeons. They have a goal-seeking behavior. And you might model them with the computer programs, differential equations, but you have to realize that this is just a substitute for what is the basic of human nature. And this is why we have what Professor Zwick called about imprecision. It is not imprecision. It is essential for complex system and for what I call cybernetics view of human, that there is uncertainty because decisions have yet to be made, and the image of the world has to change and so on. So the third hierarchy, which we use in viewing the globe, is division of labor, organizational hierarchy. And here again, it's not a question of integration. You see, the people in climate change, they talk about integration, meaning take a large atmospheric model and a large model of ocean and put together, right? It is a question of coordination, how to coordinate. And there are theories of coordination which we have applied in order to get a better feel for what is going on. Yeah, thank you. So just two more slides. One is the second obstacle to understanding, first being complexity, I don't mean the sequence, but any of the other, is uncertainty. And how we deal with uncertainty is the following. We have these hierarchies, conceptual hierarchy. We recognize independence of levels and so on. And we have some models, not integrated, large, but a set of models. And we have a decision sort of interface with the user. And we then let the user reflect on values and so on. In other words, don't model what is not modelable. So that's the way we deal with uncertainty. Now, let me then conclude with another comment. All this is very much related with sustainability, right? Because if human is indeed part of the system, what Soros refers to reflexivity, right? Then without sustainable society, there can be no sustainable development. It is not just environmentalism. It is also sustainability, what Amartya Sen refers to sustainable human development, right? Satisfying the lives not only for us, but for Africans and so on. So sustainability and global issues are two sides of the same coin. Because if it were not for finiteness of Earth and other issues, right, there's no need to worry about sustainability. And the other way around, you cannot talk about sustainability if you're only worrying whether you are using enough energy or less energy, how you're consuming and so on. In other words, it is not that you have to think globally, act locally. You have to think locally in your own best interest to be involved globally. Now, to come back to the opening statement, what we need is system scientists to work with these other scientists, right? And to see what is that we can contribute, not in terms of developing programs, right? But giving them the right perspective and right direction for their research. Thank you very much.